All right, so this one's a bit of a long one, but just be patient. We'll get through it. Basically, we're heating a substance, Z, which wasn't stated, but we're going to assume that it starts at 100K. And the reason for this is if we look at the graph that we were given, it starts at 100K. Not a great reason, but that's what we're going to play with. So the first thing is we have a solid, and anytime we're heating the solid, it's going to rise in temperature. And it's going to rise in temperature until it hits the melting point, at which point it's going to start to turn into a liquid. So it's going to stop at 200K. So our first step is to figure out how much energy is it going to take to get this substance from 100K to 200K. And since there's a temperature change involved here, we're going to use the equation Q equals M times C times delta T. And in this case, the mass of our substance is 10 grams. The specific heat, so 10 grams, the specific heat of our substance, since it's a solid, is 4. So we're going to use 4 joules per gram Kelvin. It is increasing by 100 Kelvin. So when we calculate this out, we are going to get that the heat needed to do this is equal to 10 times 4 times 100, or 4,000 joules. Now on our graph, the energy units are in kilojoules, so if we convert this to kilojoules, it's 4. So after 4 kilojoules of energy, it'll go to 200K. So going to our graph, we're going to find 4 kilojoules, which is here, and it's going to go up to 200K, so that's this point here. And we're just going to draw a straight line connecting the points. And that is the first part of our heating curve. Now once it hits 200, it's going to flatline because the additional heat needed is going to melt it. So we now have to figure out how long is this going to flatline for before it starts rising in temperature again. In other words, how much heat is required for it to melt. So our heat to melt, we use a different equation. That equation is Q equals N times delta H, where N is in moles. And we're given the molar mass of this substance, so there's 10 grams, and the molar mass is 50 grams per mole. So it turns out that we are heating up 0.2 moles. So I want to melt 0.2 moles, so I will be using 0.2 moles. Now I have 2 delta H values, and since I'm melting this, I'm going to use the heat of fusion, which is 30 kilojoules per mole. So 0.2 moles times 30 kilojoules per mole is going to give me 6 kilojoules. So it will require 6 kilojoules to melt this substance. So going back to my graph, I'm now going to go over, and I'm not going to just stop at 6 because this is how much energy it takes once it has reached the point where it can melt to melt. I need to go 6 beyond from where I was, 3, 4, 5, 6. So I can't stop here because that's only 2 kilojoules, not the 6 required. So at this point, it's finished melting, and now it's going to start going up again. And we're going to go back and use the equation we used before. So I will erase the solid part. Now it's a liquid, and the liquid is starting at 200 Kelvin, and it's going to increase until it maxes out, which is at the boiling point of 260. So again, Q equals mass. The mass hasn't changed. It's still 10 grams. Times, now I'm going to use the specific heat of liquid, which is 10 joules per gram Kelvin, times the change in temperature, which will be 60 Kelvin. So this comes out to 6,000 joules, or 6 kilojoules. And it's going to go from 200 to 260. And so we're going to graph that. So from 200 to 260, and it's going to go 6 more. So I was at 10 from before. So now I'm going to go over 6 more to 16. And I'm going to go up to 260, which is here. So that's my next curve. I'm going to go up until I hit that line. And once again, it's going to flatline as it's vaporizing. So we need to figure out how much heat it takes to vaporize it. So same equation. Q equals N times delta H. So I have 0.2 moles times the heat needed to vaporize it, which is delta H of vaporization, 55 kilojoules per mole, which will be 11 kilojoules now to vaporize it. So back to my graph, I point to where I am. I'm currently at, so I was at 16, so I'm going to add 11, and that's going to bring me to 27. So 27 is here. So this is now how much it takes to vaporize it. Notice it's a longer flat line. It usually takes more energy to vaporize than it does to melt. Now the last part you might be wondering, well, how do I know how much farther to go here? And it really doesn't matter. You have a slightly different graph paper than I have, but we can just kind of pick any point. In other words, figure out how much heat or how much energy it takes to get to a certain point. So let's say I want to figure out how much it'll take to get to 300 Kelvin, because that's sort of where I'm at on my graph. So I'm at 260 right now. So what I can do is say, okay, just like I did for the solid and liquid, I can say I'm going from 260 Kelvin to 300 Kelvin. And how much energy does that take? So once again, Q equals mass times, once again, 10 grams times specific heat of the gas, 20 joules per gram Kelvin, times, this is what, 40 Kelvin? So 10 times 20 times 40, so 10 times 20 times 40. This is going to require 8,000 joules, or 8 kilojoules to get to, this is 300 Kelvin. So going back, to get to 300 Kelvin, it's going to require 8 kilojoules. So I was at 27, so now it'll be 35, and that will get me to 300, so right here. And I can draw the line, and then once I hit it, I just keep going. I can just draw it as a straight line, and that'll work. Alternatively, I could have figured out how much energy it took, how much the temperature would change if I added this much heat and plotted the point. It really doesn't matter as long as I do one or the other. So this is the heating curve for this substance, and that's it. All right.